Hey there, and welcome to our Chem 400 office hours. Um, oop. Okay, here we go. Just getting everything lined up. Um, so good. Whoa, that is way too thin of a pencil. Last night, reason why my pencil settings are all out of whack. Last night I was indulging in some digital adult coloring books to kind of, you know, unwind, and so I was needed a finer point than I'm used to. But that being said, not good morning. This is good afternoon for sure. I hope your Friday is nice and chill. Mine has been semi-chaotic. Believe it or not, this is the I've made it to the eye of the hurricane. This is the kind of like calm moment. Oh wow. My wife normally works on Fridays, which means I am 100% full on dad mode. But this office hour is purposefully scheduled during my almost 2-year-old's nap time. So my older kids are, chill on autopilot. He's down for a nap, and I get to step away from everything and talk some chemistry, which definitely a highlight of my Friday. Let's see here. We have, I don't know why, I've been kind of vibing with these daily mixtapes. I think Song of the Day is really conducive to live in class lectures, because you're not going to throw I'm not going to write 3 songs on the board. And I'm definitely not going to write out a link to the URL to a Spotify mixtape on the board. But when you're all digital, you can link to it. So it's nice. It's called Head in the Game. It is a links in the description. It's a 3-song hip hop mix. Kind of 3 songs that I use to, like, when I'm getting my head in the game. So maybe you'll like them too. Who knows? We're all over the place. The past couple of weeks from stoner metal to hip hop. So that's that. I have. Oh, dude. I haven't logged onto my Spotify for a little bit, to like the account page. I'm obviously listening almost all the time. I'm gonna follow you back, Raj, because I always like when I'm on the computer seeing peeps I know what they're listening to. It's a great discovery tool, and totally. So, anyways, that's awesome. So as far as pre-submitted questions, I only have one today, so I'm thinking we'll knock that one out, and then I will totally hit up any live questions that we have, and obviously, I'll be checking my email and my what's that thing called, Canvas inbox throughout, to make sure that if any questions get submitted live. But our first question comes to us from I at the beginning, when I started announcing these, I said that I wouldn't disclose the identity of the students asking the questions. That way you don't have to feel self-conscious if you're like, I'm worried that this is a dumb question, which is never a fear you need to have, because as long as a question is honest, it's not dumb. But this first question came in through Canvas today, actually, this morning. And it actually wasn't a specific question. Wasn't a, can you do this in office hours? Do I have any email? No email questions today. Or just one, maybe. So this is the one that was emailed in. Again, it wasn't explicitly asked, could you do this in office hours? But I thought it would be useful, because this is I think a good example of a Lewis structure problem. So we need to draw the Lewis structure for a compound called thionyl chloride. It's SOCl2. All right, it's neutral, not ionic. We're dealing with a covalent molecule. And the specific question is how do you know? So there's going to be a double bond in this molecule. Spoiler alert. And the question is, how do you know which atom gets the double bond? Is it going to be double bond sulfur oxygen or double bond sulfur chlorine? So that was the question posed, and I answered over email, but I also wanted to, include this problem in office hours to kind of show the process, and I think it'd give us all a good starting point. So first we need to total our electrons. Sulfur has 6 valence electrons. Oxygen also has 6. Chlorine has 7, but we have 2 of them. So together our 2 chlorines are bringing 14 electrons to the party, giving us a total of 26 electrons. Now we need to pick our central atom, all right? And we always say whichever one makes the most bonds. This one's a little tricky because, as we learned in Wednesday's lecture, we know that we always pick the element that can make the most bonds, but we know that third period elements and below can all break the octet rule. They can make more than 4 bonds because they can house more than 8 electrons in their orbitals. And so we automatically go for third period, but there's a snag here. There's a catch. Both sulfur and chlorine are on the third period. So how do you pick a central atom when you have 2 third period elements to choose from? And the answer is you go back to that Lewis dot structure trick that we've been using from the beginning. If you look at the Lewis dot structure for sulfur, we have 6 valence electrons, 1, 2, 3, 4, 5, and 6. And when you look at chlorine, we have 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. And when you look at these two, when you compare these two Lewis dot structures, sulfur has 2 unpaired electrons, chlorine has 1 unpaired electron. So under normal circumstances, sulfur likes to make more bonds than chlorine. So we're going to select sulfur as our central atom. All right. So here we go. We've got sulfur. Next step, we need to attach all of our atoms to our central atom. This is going to take 2, 4, 6 electrons because we have 2 electrons in each bond, leaving us with 20 electrons in our budget left. All right. Now you can see that our oxygen has 2 electrons. We know it needs 8, so it needs 6 more, right? Same with both of both of our chlorines, both chlorines and oxygen each need 6 electrons, and 3 times 6 is 18. So we can fill everyone's octet with the electrons in our budget, because we have 20 electrons in our budget. We need 18 to complete the octet of oxygen and both chlorines. So we're going to give oxygen and our 2 chlorines 3 lone pairs each, filling out their octet. Now every atom at this moment in time has a full octet except for sulfur. Sulfur right now has 6. It needs 8, and we can give it a lone pair because we have 2 more electrons in our budget. So we have reached a point in time where we've spent all electrons, we've completed all of our octets, and you might be tempted to box this as your answer and move on. But remember, you always have to check for formal charges, right? Because we need to make sure that we've drawn the best resonance structure. And as we know, the best resonance structure will fill everyone's octet. It will have minimal formal charges, and then if you've minimized formal charges and there's still some there, it'll place the negative charges on the most electronegative element, all right? And even though thionyl chloride, SOCl2, does not have a charge, just because there's no overall charge doesn't mean that there aren't formal charges somewhere in the molecule. So we need to do our due diligence. I'm going to calculate this down here. If you calculate the formal charge for chlorine, when chlorine is neutral, it has 7 electrons, all right? 7 valence electrons. And now we need to subtract the number of electrons in the molecule. It has 1 electron from its single bond with sulfur, and it has 6 electrons in lone pairs, so 7 minus 7 is 0. Sulfur has no formal charge. Chlorine has no formal charge. And both chlorines in this molecule are the same if you calculate it out. Sulfur, when it is neutral, has 6 valence electrons. Now let's subtract the electrons it has access to in this structure. When we're calculating formal charges, you get 1 electron per bond. So we have 1, 2, 3 bonds on sulfur, plus the number of electrons we have in lone pairs, and sulfur has 2 electrons in lone pairs. So 6 minus 5 is a positive 1. That means sulfur has a formal charge of positive 1 in this resonance structure as drawn. Now let's calculate the formal charge for oxygen. When oxygen is neutral, it has 6 valence electrons. In this structure, it has 1 bond, so we get 1 electron, plus it has 6 electrons in lone pairs. 6 minus 7 is negative 1, so oxygen here has a formal charge of negative 1. All right? Now, we know that whenever we have a formal negative on an atom that's next to another atom with a formal positive, as long as one of these 2 atoms is third period or lower, as long as one of the atoms involved can break the octet rule, we can minimize our formal charge. And sulfur is third period, so we can. We minimize formal charge by taking one of our lone pairs on the negative atom and turning it into a multiple bond with the positive atom. All right, this is going to change the structure like this. So our chlorines are unaffected by this change. So each of the 2 chlorines will have still 3 lone pairs. Sulfur still has its lone pair, but now instead of a single bond to oxygen, we have a double bond to oxygen. And now oxygen, instead of having 3 lone pairs, only has 2 because we took one of those lone pairs and we used it to make the multiple bond. All right. Now, let's calculate formal charges here. Neutral oxygen has 6 electrons. In this structure, we have 2 bonds, so 1 electron per bond, plus 4 electrons in lone pairs. Its formal charge is 0. when you calculate sulfur's formal charge, it has 6 electrons when neutral. In this structure, 1 electron per bond, right? Sulfur has 2 bonds, so that's 2. Oh, what am I saying? Sulfur does not have 2 bonds. Sulfur has 4, right? A double and 2 singles, so that's 4 total bonds. Plus 2 electrons in its lone pair. So in this structure, sulfur also has 0. 0 formal charge. So this new Lewis structure has no formal charges. So it's better than the one that we first drew. Okay, Raj, you got a question. Will this be the best resonance structure because the highest electronegative? Okay. Great question. So, Raj, the answer to your question is, first, minimize formal charges as much as possible. Then place any leftover negative charges on the most electronegative element. So the order of the day is get as many of your formal charges to go away as possible, right? We're trying to combine all our negatives and positives as much as we can. If there are any left over and you can't get rid of them, then you place the negatives on the most negative and the positives on the most positive. So that's the last thing you look for. And since with this structure, we can get rid of all of our formal charges, that is going to be a better resonance structure than the one that leaves a negative in there. All right, so that's kind of our last resort. If we have to have negatives, put the negative charge on the more electronegative element. But if you can get rid of everything, that will be your best resonance structure. All right, now I want to take a moment to kind of explicitly answer. So the question that was posed to me over Canvas, which is there's that resonance structure that I drew, or the 2 resonance structures I drew, aren't the only resonance structures for thionyl chloride. So you can draw this. See, it always takes a minute to draw in all of our lone pair dots. But there is another resonance structure in which you have chlorine double bonded to sulfur. And then oxygen is single bonded and has 3 lone pairs. All right, and in this structure, you have, let's see. So let's look at the formal charges in this structure. First, this chlorine has 7 valence electrons when it's neutral. It has 1 bond, so it gets 1 electron from that bond, plus 6 electrons in lone pairs. So it's neutral. It's 7, or 7 minus 7. This sulfur has 6 electrons when it's neutral. In this structure, it has 4 bonds, so 1 electron per, plus the 2 electrons in its lone pairs. Sulfur is also neutral. And then for the final or the second chlorine, we know that it has 7 electrons when it's neutral. In this structure, it has 2 bonds plus 4 electrons in lone pairs. So here, this chlorine actually has a formal charge of positive 1. Finally, when we calculate oxygen's formal charge, 6 when it's neutral, minus 1 electron in its bond plus 6 in its lone pairs comes out to be -1. All right. So in this structure where oxygen is single bonded to sulfur and chlorine is double bonded, you can see that we have 2 formal charges, whereas the resonance structure on the left has no formal charges. So again, this is the best resonance structure because it has minimal formal charges. I should say it has completed octets. Always the most important. And this is what makes it better than the other one. And it has minimal formal charge. So if you're ever drawing Lewis structures, and you have a couple structures and you're not sure which one to go, first, make sure the octet rule is satisfied. Second, make sure that formal charges are minimized. And if you have the choice between two structures where the octet rule is satisfied in both of them, but one of them has formal charge and the other one doesn't, you pick the one without formal charges. And then third, if you've minimized formal charges in all your resonance structures and you still need to make a choice, make sure that the negative charges are on the most electronegative element. Let's see. So because sulfur's in the third group, it can have more than 8 electrons, right? That is correct. Yeah, absolutely. Because it is on the third period, it can have more than 8 electrons. So this is totally kosher and halal all at the same time. Let's see. Also, can't there also be a double bond with the second chlorine making there one more? Yes, absolutely. Absolutely. You can absolutely draw a third resonance structure where the other chlorine has the double bond. And we say that those two resonance structures with chlorines double bonded to sulfur are minor contributors because they're not quite as good as the one with the double bonded oxygen and no formal charges, but they're definitely there. They're definitely Lewis structures. So if someone asked you to draw all possible Lewis structures, you would draw all 3 of those. Totally. Let's see here. Let's see. So in the exam, do we draw all the resonance structures or just the best ones? Great question. So that depends 100% on the problem. Some problems may say draw the best resonance structure. Other problems may say draw all possible resonance structures. So it 100% depends on which on the wording of the problem that you're working. a problem could totally ask for all of them, or a problem could just ask for one, the best one. Usually, if you're wondering which ones I tend to write, for a timed exam, like for the exams during not Rona season, during normal exams, I would only ever ask for the best resonance structure. On a take-home situation, I don't know. I haven't decided yet. I would totally there. It's very, very likely that you'll get a problem that says draw the best resonance structure. But I could write a problem that says draw all resonance structures with completed octets for the following molecule. I could totally see myself doing that on a take-home test. So who knows? You'll definitely get the first one, draw the best. Whether or not you draw all, most likely depends upon how I write it, to be honest. Totally. Let's see. I am gonna check. Check some stuff. See if I have any new questions coming in. Let's see, none in the email inbox yet. Oh yeah, totally. I remember that problem in the lab exercise. There's one. They don't ask you to do it for each one, but there is that one problem where they say draw all possible resonance structures for this dude. And normally I can give the condolences of like, I wouldn't do that on a test because it's timed and and it's short. But when we're talking about a 24-hour take-home, it's totally something I could see myself doing. So you'll have to get over the lazies. Let's see. Are we going to cover? Yes, absolutely. So, Monday we are going to be covering Vesper. Between Monday and Wednesday next week, we are going to be hitting up all of Vesper theory, and then an intro to hybridization will probably hit hybridization the next week. Yeah, at this point, you can draw all of the Lewis structures, and after next week, you will be able to assign the geometry, bond angles, and hybridization. So yeah. It asks for all their 6. Totally. Do you need help finding them? Because I am here to be helpful. At least I try. Whether or not I succeed, that's a different story. And at this point, we don't have any fresh questions, so I'm down to hit anything you guys have. Yeah, Raj. So here's what I would do. With the lab exercise. So I believe it's exercise 5, right? So they ask you to draw the Lewis structures, do geometry stuff, and 3, they ask you to do hybridization. Stuff. All right. So you can't do 2 and 3 yet, but you can do draw the Lewis structures. And if I recall, for the geometry and hybridization stuff, I believe they ask you to label. So what you can do is, what I would recommend is draw all the Lewis structures. Now, I would go through and draw all the Lewis structures. And then, after lecture on Monday/Wednesday, then you can go through. Go throw. You can go through the Lewis structures and label the geometry/hybrid stuff. All right. And then finally, you can hit up Friday office hours for help with the hard stuff that you aren't able to do on your own. And that is your 3-step path to victory for exercise 5. All right. We have not. Yeah. Totally. So, we have not yet covered geometry. Trees, or electron, domains, which some people like me call them electron groups. That'll be Monday and Wednesday lecture next week. Totally. Okay, so you said you're done with most, but you weren't sure about N3. Would you like me to do N3 minus? I totally can. If you'd like me to. All right, let's do it. Okay, so with this example, we're asked to draw all the resonance structures for the following polyatomic ion. So before we can draw all the resonance structures, we need to have a Lewis structure for this dude. So let's get one. Nitrogen has 5 valence electrons, but we have 3 nitrogens in this molecule, so that gives us a total of 15. And in addition, we have a charge of -1, which means we have 1 extra electron up in this mix. So we have a budget of 16 electrons. Picking a central atom is easy because all we have to choose from are nitrogens. When we connect our 2 nitrogens to the central one, we spend 4 electrons, leaving us with 12. All right. Now you'll notice that the nitrogen on each termini needs 6. So we can spend 12 electrons to complete the 2 terminal nitrogens octets, but that bottoms out our budget. We have no more electrons to spend, and our central nitrogen at this moment in time needs 4 more electrons. Right? And so from this point in time, this is this moment, this step in drawing the Lewis structure for this molecule. This will give us all of our possible resonance structures. Let's see, we're going to have 3. All right. I'm going to go to a new slide. I'm going to redraw this structure as is, just on a new slide. All right, because this this Lewis structure isn't done, but this incomplete Lewis structure will get us to all 3 resonance structures. All right, so we can get 1 so this, we agree that our central nitrogen needs 4. If we take 2 lone pairs from our nitrogen on the right, and use those to make multiple bonds with the nitrogen in the center, that will give us 1 resonance structure. All right, this will give us a resonance structure where we have our central nitrogen triple bonded to the nitrogen on the right, and our nitrogen on the left has 3 lone pairs. All right. If we do the same thing but with the nitrogen on the left, take these 2 lone pairs and use them to make multiple bonds with our central nitrogen, this will give us another resonance structure, one in which the nitrogen on the left is triple bonded to the central nitrogen. All right. And triple bonded to one, single bonded to the other. That is our second resonance structure. Our third and final is, instead of one of the terminal nitrogens taking care of the central one by itself, if we take 1 lone pair from one and 1 lone pair from another, and they each give the central nitrogen a multiple bond, we're left with our central nitrogen double bonded to each terminal nitrogen, and each terminal nitrogen having 2 lone pairs. All right. Now, if you look at your formal charges, we can calculate all of these. I'm going to do them really fast. Here, nitrogen when it's neutral is 5. Minus, we got 3 bonds, 2 in lone pairs, so that guy's 0. This central nitrogen, we know that it has 5 when it's neutral. It has 4 bonds, no lone pairs, so this is a positive 1. And then our terminal nitrogen, we know it has 5 when it's neutral, minus 1 in a bond, 6 in lone pairs, so it comes out to be negative 2. So this Lewis structure has negative 2, positive 1, and neutral. It's going to be the same thing for the one all the way to the left. We're going to have a negative 2 on this nitrogen, a positive 1, and neutral. Then finally, in our central structure, this nitrogen in the center, when it's neutral, it has 5. It has 4 bonds, so it comes out to be positive 1. And then both nitrogen on the termini, both terminal nitrogens, have the same number of electrons in the structure, so their formal charges will be equal. Each one has has 2 bonds, so 2 electrons from each bond, plus 4 electrons in lone pairs, so that comes out to be a negative 1. So this central one has 1 formal positive and then 2 formal negatives each on their terminal nitrogen. So these are the 3 resonance structures for the azide polyatomic ion. That's N3 with a negative 1 charge. If you had to pick the best one is actually going to be the central Lewis structure, because we know that negative charges don't like each other, right? So 2 negative charges don't like hanging out on the same atom, and both of the Lewis structures where nitrogens, one of the terminal nitrogens has a negative charge of 2, would put 2 negative charges on the same atom. They would rather be spread out. So the central one would be the best, and these would be the 3 Lewis structures. And it's like you already knew that. Well done. So these are the 3 resonance structures for azide for this polyatomic ion. Okay. Let's see. Okay, so for SCN, I only get 1 resonance structure. Is that possible? Okay. Okay, so here's the thing. And so we'll do this one. It'll be good rep. I believe there is one best resonance structure. I believe there's one best resonance structure, but several possible resonance structures. And you'll see what I mean in a second. Let's do this one. All right. So for SCN, sulfur brings 6 electrons. Carbon brings 4. Nitrogen brings 5. And then our charge of -1 brings an extra electron to this party. So we have, let's see, 16 electrons. Now, for this structure, excuse me, so you're going to attach sulfur and nitrogen to your central atom, which is carbon. And now you may be going, wait. Sulfur's a third period element. And we always pick our central atom as the one that can make the most bonds. Sulfur can make the most bonds. That is correct. So with this particular molecule, carbon's actually the central atom. I wouldn't test you guys on this because this is something that deviates from the norm and the rules that I gave you. The rules that I gave you for drawing Lewis structures kind of lays out the general norm. This is a compound that you'll run into in Chem, and so it'll make more sense to you if you take it then. But I wouldn't be testing you on examples like this. So don't freak out. You don't have to memorize it. It wouldn't show up on the exam, but I feel duty-bound to draw this structure as it is. And so, carbon's essential on this guy. Now, we have the exact same situation as we did last time. We can complete the octet for nitrogen by spending 6 electrons, leaving us with 6. And completing sulfurs spends the remaining electrons in our budget. Well done. Yeah, you definitely want to roll with carbon in this one. And you'll notice we're in the exact same predicament that we were last time. All right, and so the question is, how do we satisfy carbon's octet? And we do so. We satisfy carbon's octet by taking lone pairs, turning them into pi bonds. So we'd have triple bond N would be 1. We could also do the same for sulfur. Take 2 of its lone pairs and make it a triple bond. Oh, I forgot my lone pairs on sulfur. So this would be, we'd have an S triple bonded to C. And nitrogen keeps all its lone pairs. Or we could take our 1 lone pair from each. And make sulfur and nitrogen each double bonded to our central carbon, leaving them with 2 lone pairs of pop. All right, and for clarity, I'm not going to show the calculation for formal charges for each of these. I'm just going to assign them. So in the first one, carbon and nitrogen are neutral. Sulfur bears a -1. For the middle one, sulfur and carbon are neutral. Nitrogen bears a -1. And then for the final one, sulfur is +1, carbon is neutral, and nitrogen is -2. All right, so these would be the 3 resonance structures for this molecule that are all resonance structures of each other. And the worst one is this guy down here. It's the worst because it has the most formal charges, which I'll abbreviate as FC. Between the other two, actually, there's a trend that we haven't learned yet. And sulfide, which is sulfur with a negative charge, is actually more stable than nitride. So the true answer is the best one is the one on the very top, the one that's with sulfur. And you're like, wait a minute, sulfur has is less electronegative than nitrogen. Again, we haven't learned this trend. You will learn it in organic chemistry, so I wouldn't test you on that. For this molecule, there's several things about it that would keep me from putting it on an exam. So, but these are the 3 resonance structures that they're looking for when they ask you draw all possible resonance structures. So hopefully that makes sense. One that I would totally give you So I would totally give you this molecule and ask you to draw all possible resonance structures So draw all resonance structures plus I'd ask you to pick the best. For this molecule, I totally would. So if you want to see a similar structure, similar process, but one that I would put on the test, that one, OCN, I absolutely would. So you can give that a try when you're bored this weekend. All right, let's take a look to see if anything new has come through. Let's see. Okay, so the way I did it was sulfur is a higher group, thus can hold more negative charge. That is not a bad way to think about it. The real reason is sulfur is in a higher group, or in a higher, or sorry, is on a lower period, so its orbitals are larger than nitrogen's. Larger orbitals means there's more room for the electrons which means they have less chance of bumping into each other. Whoa, I almost hit 192 characters. Almost hit the cap. Nope. Carbon likes to make more bonds than oxygen. Yup. Carbon is a dope central atom. Totally. Sorry, I'm checking the old emails to see if there's anything new coming down the pike. Ooh. Which it doesn't look like there is. Kind of a lightly trafficked, what's the word I'm looking for? Office hours today. Let's see. Okay. Okay. So when you look at you run through it and you do all the stuff. Whoa. You'll actually notice that we get 3 very similar Lewis structures here. So we get this guy. We get the opposite extreme. Then we get this guy. Or here, I'll draw him. Down here, one where we've got both of them double bonded. Oh, carbon's in the middle. And when you calculate your formal charges, in that first one that I drew here, oxygen's got a negative. In the second one down here, nitrogen has a negative. And in the last one, oxygen's positive and nitrogen's negative too. All right, this guy clocks in third place. All right. Most charges equals the worst. But when you look at the other two, one puts a negative charge on oxygen. The only difference in formal charges is this. And then the other puts a negative charge on nitrogen. And oxygen is more electronegative. Oxygen is more electronegative than nitrogen, which makes this number 1 and this guy number 2. Hey there, sorry, I am back. I apologize for that. What, that had to be like an hour lag in the feed. I had an emergency phone call that I had to take looking at it. That was 50 minutes ago. I apologize. Things in the stream seem to be slowing down. Totally. Oh my gosh, you're still here. Raj, you are a champion. I would have pieced out on myself if I were watching this feed. Are there any other questions I can help you with? Heaven knows you deserve answers for hanging out this long. Holy moly. Anyone watching this feed, I'm going to have to put like in the comments, not comments, in the description, when I timestamp everything, it'll be like dead space, 50-minute gap. Oh, oh man. Well, I mean, props to you for having big brain. I apologize for the abruptness of that. Other than Vesper, yep, that is correct. We're going to be covering Vesper and geometries, electron domains, all that good stuff on Monday. Between Monday and Wednesday. And then actually we're going to be getting to like kind of a full-blown explanation of hybridization on probably the following week. But we will learn enough hybridization to finish exercise 5 by Wednesday. So with those 2 next lectures, you'll be able to do all the problems, or at least attempt all the problems in exercise 5, and then we'll have Friday's office hours to hit any parts of exercise 5 that are still confusing. Totally. Well, Vraj, this has kind of been like just a personal hangout between you and I. It will probably get more traffic on the rewatches, but as far as the live business goes, it's just been the two of us. I do have one question, however. What is your Spotify? Your Spotify handle. I want to follow you back. I actually went in a couple of the dead zones. I was low-key searching for it in Spotify, and I found two Vraj Thakars, but neither of the pictures looked like you. So it made me wonder if you're nice. Okay, that's why I was looking at these pictures and I'm like, neither of these look like the Vraj I know. There we go. All right, now we're hanging. Awesome. Well, I look forward to seeing you showing up in my friend activity feed. Totally. Well, I think I'm going to conclude our stream there. Raj, thanks for hanging out, and thanks to anybody rewatching this stream. I apologize for the gigantic dead zone, but feel free to watch your way through that blank, unchanging screen. Yeah, maybe. Mine, you can kind of tell it me because of I got that little like cartoony version of me that I don't know, I feel like is a fairly accurate representation. I did not draw that myself. That was my brother, is a visual artist, graphics design person. He did that for me. I feel like it's a fairly accurate portrayal of me with my little faux hawk, but so hopefully you can tell it's me. But yeah, I could not tell, and would never have guessed to search Rajjashi 5. But now I have, and now we buds. Anyways, thanks, Raj, for watching live, and anybody else who watches later afterwards. I will timestamp this thing so you can find the good problems, and I will catch you all on Monday. Yeah, I think it is pretty cool. Oh yeah, no, there's no way I'm that talented. Though, oops. The one thing I did add, though, when he originally did this, I didn't have the current glasses style that I did. He just drew me with no glasses. And then I took that image at a later point once I got these glasses, found them online, and then added them to the picture. So I had a little contribution. I did the glasses, but the actual original art is my brother. Who, if you want to see his good work, you can find him. I never, with his handle, there's an underscore in it, and I never remember exactly where it lands. There we go. You can find him on the Instas. As wind up _ skeleton head. This stuff is pretty rad. So if you're bored and you want to see some excellent drawings of weird monsters, happy little cartoon dudes, and just all sorts of stuff. He does webcomics a little bit up there. It's some really... I'm a huge fan, not just because he's my little brother, but because his art is varied and visceral and emotive, and, you know, I can't say enough good things. So you should go check it out, because a picture's worth 1,000 words, and he has 510 posts, so that's worth 510,000 words, if that adage is true. So anyways, that's our office hours for today. Thank you, Viraj, for participating. Other people for watching later, and I will catch you all on the flip side for Monday morning's lecture. Later.